Okay, friends. So, in our previous lectures, we have seen that how the linear and quadratic Newton's interpolating functions are used. We have solved a couple of examples. Now, we will see the more general form of evaluating the Newton's interpolating coefficients. So, general form of this function is, let's say, n minus 1th order polynomial function which passes through n data points. So we can write f of n minus 1 x b1 plus b2. This is a special form of writing the Newton's interpolating function. This is a general form. Interpolating polynomials. Then b3 x minus x1 x minus x2 and bn x minus x1 x minus x2 x minus x of n minus 1. So of course there are data points and functions value. There are data points which can be written x1 f of x1. This function passing through this data point x2, then f of x2, x3, f of x3. So we use this actually to evaluate the, we have also seen to evaluate this b1, b2, b3. We have used these data points. Okay, so using these data points, you can evaluate the coefficients. Okay, so b1, we have seen b1 is f of x1, b2 is f of x2 minus x1, b3 slightly different notation, we are using x3, x2, x1, and bn, what we are writing is the general form. bn is f of xn, xn minus 1, x2, x1. This bracketed, function evaluations. This name of these is actually nothing but finite divided differences. This is very important terminology. Finite divided differences. Newton's finite divided difference. We have seen the linear and quadratic case where we have obtained the value for, just for your sake of repetition, I am writing this. This was the value for, of course, f of x1. Then second was f of x2 minus f of x1 divided by x2 minus x1. And the third value which we have evaluated turns out to be for b3 was f of x3 minus f of x2 divided by x3 minus x2. We have slightly rearranged this term and derived f of x2 minus f of x1 and divide by x2, x2 minus x1, and the whole term divided by x3 minus x1. So this was about this. So can we write it in a slightly different version, that finite divided differences can be represented in the form of f of xi xj, the bracketed value xi xj is equal to f of xi f of xj divided by xi minus xj. Similarly, we can write f of, what we are writing is divided difference is general form because it is going to help us in deriving these coefficients. We can directly write these coefficients and then put it in the general form of Newton's interpolating formula to evaluate the function's intermediate value, where we want to determine the function's value at some other data points other than these given data points. These are given. So we can write like, for example, in this case, we can, that this is nothing but, f of basically the slope, x3 minus x2, so that means x3 x2, and this we can write f of x2 x1, and difference of that and divide by, x3 minus x1 will give you the coefficient, and this is called as divided differences. Then xj, then xk, and we can write the differences f of xi xj minus f of xj xk, and then xi minus xk, general form. But simplified version, when we have fixed data points, we have written like this. Okay. Now I told you these differences can be used to evaluate the coefficients and to yield the general form of Newton's interpolating function. Now, in order to understand this use of this, we will take the same example we have taken in our last class. Let us say we have the data points x1 is equal to 1, x2 is equal to 4, x3 is equal to 6. To estimate ln 2, okay, with a parabola. Now we will be adding, we have use a quadratic Newton's interpolating function. We have actually derived these coefficients. This was your b3, this was your b2, and then b1 is function's value at x equal to x1. But now we will be adding the fourth data point, that is x4 is equal to 5. And we try to use this formula. Of course, f of x4 will give you 1.609438. This is nothing but ln 5. Okay, function's value at 5. And we want to, our objective was to determine, function's value at 2. So these four data points are given. X1 is equal to 1, x2 equal to 4, x3 is equal to 6, x4 is equal to 5. And we want to estimate ln2 with the third order Newton's interpolating polynomial. So third order Newton's interpolating formula can be written in our general formula. We will write n equal to 4. So our general formula was this. Here we will substitute n equal to 4 because we have n data point. It will give you third order polynomial, okay, n minus 1. So substituting n is equal to 4 into this, we will get the third order Newton's interpolating formula, b1 plus b2 x minus x1 plus b3 x minus x1 x minus x2 plus b4 x minus x1 x minus x2 x minus x3. So first divided differences can be, there are steps, there are steps, first, second, third. And if we have 4 data points, I will draw one table which will help you in writing the, systematic way of doing it. Let us say x1, x2, x3, x4, 4 data points, then f x1, f of x2, this is also available, x3, f of x1. So first divided differences, then second divided differences, and third. So first one is always written as x2, x1, x3, x2, f of x4, x3. So basically this follows. This is going to, this will help use these two functions value. This is going to use these two functions value. This is going to use this two functions value. And the second divided differences can be written the function of x3, x2, x1, f of x4, x3, x2, and you can see here that this is going to use this formula. Third one, f of x4, x3, x2, x1, the final one. So first divided differences will be written. We will write all these three formulas and evaluate our equation. So f of x2, x1, f of x3, x2, f of x4, x3. So this is written ln 4 minus ln 1, 4 minus 1 because x2 and x1. The values are given for x2 and x1. x1 equal to 1, x2 equal to 4, x3 is equal to 6, x4 is equal to 5. So we will be using this formula. The formula which we have written, we have used the general formula. This formula. We'll be using ij, let's say 1 and 2. I is equal to 1, j is equal to 2. So this way it can be written. Then ln 6 minus ln, we are going to use 3 and 2. So 6 minus 4. 4 and 3. You can, instead of ij 1 2, you can write 2 3 and 3 4. So it will be like we have used this formula x2 minus x1. Similarly, you can use x3 minus x1. That is the first divided differences. x3 minus x2 divided by x3 minus x2. F of that. So it is going to give you this formula ln 5 6, 5 minus 6. So this will give you 0.4620981, 1.791759 minus 1.386294 divided by 6 minus 4. It gives you 0.2027326. And the last one I am writing direct answer 0.1823216. Now the second divided differences. Second divided differences is similar to this, and you can see here it is using the first divided differences already, which we have already determined. So it is using x3, x2, then x2, x1, and so on. So we'll be using these three evaluated values for that. So second divided differences. F of x3, x2, x1, and it can be f of x3, x2 minus f of x2 x1 divided by x3 x1. Similarly, f of x4 x3 x2 can be written as f of x4 x3 minus x3 x2 and x4 x2. You can easily remember also this formula. Then f of, we can evaluate these two by substituting functions value which we have already determined. So you can substitute this value x2 x3 x2 here, then x3 x2 x1 here, and similarly you can determine x4 x3 substitute here, x3 x2 substitute here. So we are getting, I am writing the final answer. You can evaluate yourself. That is minus 0.05187, sorry, 0.05187,311 minus 0.02041100. And the third divided differences can be, this was the second divided differences. Third divided differences can be written as f of x4 x3 x2 x1. And this was, we already seen in our earlier cases. Actually, this minus this. The differences of third divided differences. Okay. So you can check that it turns out to be f of x4 x3 x2 minus f of divided by x4 minus x1. x1 is 1, x4 is 5. So by substituting values, we are getting minus 0.02041100 minus 0.05187311 divided by 5 minus 1. It gives you 0.007865529. So you can make the divided difference table, and finally the interpolating coefficient. What we have determined is the ultimately you have to write the interpolating coefficients, that the final equation can be written in the form of, instead of b1 we will write b1 plus, instead of b2 we will write x2 x1, then x minus x1, plus you can write b2, b2 is here, b3, x minus x1 x minus x2, so instead of b3 you can write f of x3, x2, x1, and plus b4, x minus x1, x minus x2, x minus x3. Instead of b4, you can write f of x4, x3, x2, x1. And this was, of course, f of x1. So by substituting all the values and known values, these we have already evaluated. The first divided, then second divided, and third divided differences. Okay. Whatever values we are getting, we are simply substituting. Then substitute value of x1, x2, x2, x4, and then substitute value of x equal to 2 finally to get the answer. So you are getting the function's value at x1, that is x1 equal to 1, gives you ln 1, because x1 is 1. Ln 1 will give you 0 plus, I'm simply substituting the first divided differences. What we have obtained, x2 0.462091. The first divided differences of x2, x1. So 0.462091 minus 0.05187311 into x minus 1, x minus 4 plus 0.0078655529 x minus 1, x minus 4, x minus 6. And this should be evaluated at x equal to 2. And the answer you can see here, it turns out to be 0.62876686. F of x2. X equal to 2. And if you calculate the relative error, it turns out to be 9.3%. This is much smaller as compared to, linear and quadratic interpolation. So you can generalize to get the closer values of your functions.